Hello students, we're here today and we're going to start to run our mechanics lab. So we're using a vintage 1950s real universal testing system. It's a very, very nice machine. We're hopefully going to be getting a new Instron soon. But in the meantime, we're going to still be able to do all of our cool analysis on this machine. So we've powered it up over here. As you can see, we have our dial switch, we have our power on. We have basically our jog functions. So load will basically move the jogs, the grips further apart. Unload will actually compress the system. We have basically a low and high, basically strain rate system where we're gonna control that strain rate and to run at basically at 15 millimeters per minute. So right now we are going to run a sample. And actually, where is our sample? Let's go ahead. Let's take a peek. Where did that sample get to? Well, actually, we can go ahead and we can see, as we take our nice little tour here, we can see a sample that we're gonna run. And we're gonna actually run a sample that is polystyrene. So it's an amorphous polymeric material. We're using basically cylindrical samples, tensile specimens. Sometimes they use flat dog bones, but here they're threaded and they're gonna thread right into, as you can kind of see here, we're gonna thread these directly into our grips. So we're just gonna feed those in basically almost the full length, so we make sure we have a nice secure essentially grip here. We'll jog down now the machine until we get close to here, and I'm actually going to kind of unscrew this. I'm unscrewing it because of the following reasons. One, it's gonna make it easier for me to actually screw in and secure the sample one-handed. You should always use two hands here. And you see that this can actually scroll up, so it'll reduce any incidence of, you want to avoid having your fingers in a place where it can be compressed, so we want to avoid those pinch points. So, again, we're in low gear right now. We can actually increase to high gear. We are always at a low value here to start off with. We're going to unload because we want to bring those grips higher. And you're going to see very loudly, and maybe it's hard to see in the video, but these are actually turning. They're turning very slowly, but they are indeed turning. So we'll be back once we get you to the next, so we start to secure the clips. Just an update, you can see we're getting close to where we're gonna have to screw in here. I won't be recording that because it's a little bit, I think having two hands will be great. So you'll see it when it's just finally fully screwed in essentially to our system. All right, so we are back and we have our polystyrene sample nice and tightly inserted in here. For our actual test, we're going to take data with an extensometer, so we don't really have to measure the initial gauge length. But if you're doing an old-fashioned measurement, you would essentially measure your gauge length. So that would be the initial length of your sample with the micrometer. This is going to be a little bit, it'll be fine if you're looking at ultimate tensile strength, yield strength, some of those values, but for calculating a Young's modulus, there's gonna be an initial error because of that first couple, you wanna be really, really, really accurate in those first couple of steps or displacement of your jaws. So an extensometer is gonna be really the best way to essentially measure those values. But we are using this to kind of just get a sense today of how we're gonna run this experiment. So we have our system in the stop. We are in low, so we are going to basically flip this and start to load it, and we're going to keep it at our highest rate to get to that 15 millimeters per minute. So we're going to press load. Actually, we'll go ahead and switch, and then we're going to press load, and we're going to start. We have a range selector for the basically amount of load that we anticipate. So we're at 30,000 pounds here. And now you can see that needle start to move. So we're actually loading our system. So you see that the value is going to shift as we continue to increase the stress placed on our system. So again, we're moving 15 millimeters per minute apart, and we'll see how our system responds. So this is polystyrene. It's a fully amorphous polymer. So we're just gonna sit and wait for this sample, and we'll show you some snapshots of another polymer sample, and then we'll leave the metals to your imagination. So we wanna look for the point on our stress strain curve when our engineering stress starts to flatline and decrease. That will correspond to when necking occurs in our system. So we'll be able to see when that cross-sectional area thins, and we'll be able to analyze the system. So for right now, nothing too exciting to write home about just yet. So again, we can see on our old dial system. In the new system that we're about to get here at Cal Poly Humboldt, we're about to get an Insteron that is going to greatly increase the number of tests and the variety of tests that we can do. So fatigue testing, some bending tests, obviously uniaxial tension, uniaxial compression. So it's going to be a pretty exciting time. But even then, you can still get some great insights into the mechanical properties of materials, even when you're just looking at systems like this. So we'll check back in when we start to see the neck occur. Or actually, we'll keep rolling. But I may go silent here. So our stress value is kind of stalled out. You see it still, it's not decreasing quite just yet, but it's starting to. And it may not be possible to see on the video yet, but there looks like some instabilities for a neck start will be start to, it looks like in real space, in real time here, where there can be some instabilities where a neck will start to form soon. But this is kind of the difference in polymeric materials versus metallic materials in terms of the mechanical properties. Obviously, polymers are, in general, much more ductile than metals. Even polystyrene, and actually, I don't know if you can see this here, the colors have started to shift too, because you're looking at essentially chain elongation and alignment that is not indicative of the fully amorphous polystyrene. So that is something to examine and look at. And you can almost see that neck starting to form here, but the color change is really interesting. A polystyrene is a fully amorphous material, meaning that the polymer chains are like kind of arranged in a spaghetti-like structure, completely random coil, whereas a semi-crystalline polymer like polyethylene, high-density polyethylene in particular, they are going to have regions that are highly aligned, like lamella structures, which is like dried ramen. Now, when those chains are pulled apart, they are going to elongate, similar to how this polystyrene is, but because of those crystalline regions, they can actually start to recrystallize and stabilize the neck as it's pulled. Whereas this material, you'll see once it starts to form the neck, failure is going to be coming soon after. So you can actually really start to see it now. It's about a little bit halfway down there. I think I'm getting a good visual of the neck, but the neck is starting to kind of form here. So we should imagine to see neck and then afterwards. One of the things that is missing on this apparatus is kind of a shield. So it's great. This is great for showing you videos, but whenever you're running a tensile test or any mechanical test, you should have an enclosure that will prevent you from basically, have any shards fracturing. But again, we are going to be at a safe distance, and we are going to be wearing our eyeglasses, so there's no concern about that. Safety is a huge priority, in particular because these grips are being loaded with a considerable amount of force. that remains in those grips while the sample is still intact. So please be cautious when you reach, really try to avoid at all reaching into the sample when it's loaded. So if it doesn't break under your system, it still has that tension there, so be cautious. And you can see that neck really starting to form now. And you kind of see, that was our max value stress. You see the stress is creeping back and slowly decreasing now. So you can effectively see that neck starting to form. Nice picture in there now. Again, we're just going nice and slow. But you see that change in color as well because of the chain alignment. You'll really see it once we're basically off of our sample. And you'll look at basically the sample in the grips. Remember, it was dark black when we first started our experiment. And you can see essentially that neck occur. So we will see some fracture behavior soon, but you can see that neck. Oh, I can see some crazes starting to actually open up here in the system. It's just really nice. So some little surface tearing. Hard to see, impossible to see on the video, but if you're in person, actually, let's try. Oop, there it went. And we saw it. So you can see your fracture pattern right there. I'm glad I didn't yelp, but I'm sure I was a little bit shocked at the video. But that's what we got. So let us, actually, we'll let it keep going because we want to unscrew it. But you can see that fracture right here. And it is indeed, I mean, it's still a ductile fracture, especially compared to metals and ceramics. But for polymers, you'll see that is a fairly brittle transition. Even though we still see the neck and all of those good things. So this is our polystyrene fracture. So I'm going to go, and I think that this is enough room, hopefully. And if I said don't do this. Yeah, I think we should. Let's just give it a little bit more room. I could actually start to unscrew just to get a sense. Yeah, let's wait for a little bit longer. Actually, I'll screw this down further. Let's see, because I want to keep my fracture pattern nice and wiggly. Yeah, just a little bit more. Patience is a virtue. Let's go. Start to just a little bit more. Oh, we're so close. The Instron, the nice feature is you can kind of jog up really quickly when the test ends. So we could switch it right now to high mode, but I want to make sure, again, we need to make sure this machine is very, we can't have this machine fail. But it's a really cool fracture, and I hope I didn't, when I was a little bit shocked at it, hope I didn't screw up the sample. Oh, almost. Just tighten it up there. There we go. Oops. So let's go around. I'll stop the test as well. But I'm just gonna slow it down. I'm gonna stop it. And we can now, even though I grabbed it. Oh, look at that. It's beautiful. Amazing. So you see in the grips, much darker because it's not elongating, but you can see that fracture tip right here. Gorgeous. Definitely ductile, but again, for polymers, that is a somewhat brittle fracture pattern. Now, you could take a whole course on basically fracture patterns and essentially material structures, but you can see for a polymer, it did not extend significantly prior to fracture, at least for an amorphous polymer. So let's compare that with polyethylene, high-density polyethylene, which we'll see right now. So we're back with polyethylene, and it was not able to fracture in our system. And just look at the difference between these two different polymers. All we change in the chemical structure is a styrene unit, and look at that behavior. Brittle fracture, neck stability here because of the semicrystalline nature of this polymer, high-density polyethylene versus this polymer, and we're good to go. Amazing. So good luck on your lab, and let's get to the analysis in our next video. Thanks. Bye.